asked me to talk about Julia, which I found a little bit surprising since I feel like I was not necessarily Colorado's expert, but he assured me I am. So here we go. So my background is different than probably a lot of yours. I'm a physicist at NIST in Boulder, Colorado. And I assured my colleagues that you guys would not get away without hearing at least a little bit about what I actually do before I get to the thing you're probably interested in. So this thing here on the left is a ultra low temperature detector array. This is what I and my group work on. So up here at the top, there's some pixels, and then down here on the side is a bunch of readout electronics, basically. And everything here gets cooled down to about 1/10 of a degree Kelvin, and then we get signals from the pixels. They get amplified through these superconducting squid amplifiers, and then we have a bunch of room temperature electronics. And eventually we get something that looks like this, which is, you can think of this as time and temperature. So this is just temperature versus time. They're calorimeters, so something is hitting our pixels, and that something is an X-ray, and it's heating them up, and then later they cool back down. And the height of how much they heat up is basically proportional to how much energy there was in the X-rays. And so we can start to do X-ray spectroscopy with this. And so I end up with a bunch of things that look like this on my computer. Today I'm getting sort of hundreds of millions of them per day, and we're expecting to improve the hardware such that we're going to be getting a few more orders of magnitude over the next few years. And so that's really where my interest in computing comes from, is trying to figure out how much energy are in pulses like this. So I'm going to start with an oversimplification of the history of scientific computing. And I don't know, I guess from what I was hearing in this talk, I think maybe some of your interests are a little bit different than how I think of scientific computing, so hopefully it's not too confusing if I use different words. But so the simplification goes like this. C and FORTRAN are static and fast, where static is sort of code for a pain in the butt, and but they're fast, so that's really good. And then there's these new languages that came along to save scientists who don't really know the program all that well, and they're easy to use, but they're slow. And this is Python, R, and MATLAB, and I'm sure there's a million more. But it's okay that they're slow because you don't actually use anything that was written in Python. You just string together functions that somebody else wrote in C. And so as long as you can vectorize all of your code, you can call out the functions that were written in C, and you're not really paying a huge penalty. And that works as long as you don't run into a problem that you can't vectorize, in which case then you have to go back to C and you have a two-language problem. And so Julia is basically trying to solve this. It wants to be dynamic, so it'll feel like Python or R when you're programming in it, but it's going to be fast, so you can compile it and get C-like performance out of it. That is the goal. And so since that's the goal, let's see if I can convince you that they're at least somewhere there. So this is a set of benchmarks that the Julia developers put together. You can see there's a bunch of names of algorithms over here. And they implemented them all in C and then in a bunch of other languages. And C on this plot is this line here, which is 10 to the 0, 1. And everything is timed relative to C. So you can see Julia is sort of clumped around 1, so that's pretty good. The sort of informal goal is that you should be able to get about within about a factor of 2 of C performance in most cases with Julia. And you can see that, at least for this subset of algorithms, they're doing a pretty good job. And then you can see these other programming languages I was mentioning, like Python, and R, and MATLAB, are over here, and they have things in the order of 10, or sometimes 10 to the 2, compared to C. And if you read about this set of benchmarks online, you'll find a little bit of criticism, which people say, well, they didn't use best practices in R. They didn't use best practices in Python. Where those best practices might include, like, writing a C function. So what they'll say is, basically, we essentially went to Wikipedia. We looked up the pseudocode for the Mandelbrot set, and we implemented that. And that's what we're comparing. We're comparing, you just do the straightforward implementation of these algorithms. And so I mentioned the Mandelbrot set. Let's look at what the code looks like in Julia and Python and FORTRAN, just to get a sense for what this language looks like. So here's some Python here. You can see it's pretty short. There's basically a for loop, an if statement, a little bit of math, and then it might return something. And here's some Julia. And I really hope the text is big enough that you guys can read it. It basically looks the same as a Python, but there's some end statements. Instead of relying on semicolons and tabs, we use end statements. But other than that, it basically looks like Python. And then we have over here FORTRAN, and you'll notice up at the top there's something that looks fairly different. There's this word integer and complex, and I don't even know what intent means, and then another complex and integer. So basically, in FORTRAN, you're giving a whole bunch of information to the compiler about what the types of the variables are. You're saying this variable is an integer, use 64 bits to represent it, and don't ever do anything different. And that is really why FORTRAN, one of the big reasons that FORTRAN can compile to such fast code is because the hardware, or the compiler knows exactly what it needs to do, and it just does the minimum amount of work. And so now that leads into my question, like, how is Julia so fast? And a better question is really, how can Julia be so fast? Because in any language, I'm sure you can figure out how to write relatively slow code. And the answer is basically what we saw with FORTRAN. It's just types. You need to let the compiler know what you're actually trying to do and let it use the hardware efficiently. And so there's two things that the Julia team has focused on to make this an easier project than it might be if you're just trying to do this in Python, which people are. There's projects called Numba and PyPy to do basically the exact same in Python. But the Julia developers would argue that if you start with a language that's designed with this in mind, your problem is a lot easier. And so the first is type inference, which basically just means that the compiler and the Julia infrastructure can look at functions and figure out what their return types are, and it can figure out what the types of the variables are and make good inferences there. And the second is type stability, which means that when you write Julia code, and especially when the developers write Julia code, the goal is that a function should have, if you put in a given type, you should get out a given type. The return type should depend only on the type of the input, not the value of the input. And so an example here is square root. I'm taking right here the square root of the number 1, which is an integer, and I'm getting out the number 1.0, which is a float 64. Then I'm taking the square root of -1, and I might like, for convenience purposes, to get back a complex number, because that's the right answer, but Julia will give me an error, because a complex number is a different type than the floating point, and just imagine for a second I was trying to take the square root of every element in an array of integers. If I know that I'm always going to get a floating point out, I can allocate 100, float 64 spaces in memory and just fill them up one at a time. But if I know I might get a complex number, I have to check every single time. And a complex number is bigger than 64 bytes, so I can't even know exactly how much memory I need. So things just get a lot slower. So that's really the basic design behind why Julia would be fast. But I also said it's supposed to be a dynamic and fun language like Python, so I'm going to go through some of the other things that are in it. Well, first off, it's free and open source like Python and R, and I guess Spark. And it has a built-in package manager, which I consider a pretty big plus compared to trying to figure out, like, of the 10 ways to install things to work with Python, which one should I use? I don't know how familiar you guys are with IPython, but it's really popular with scientists. It basically, the default Julia interface is very IPython-like. And then it's easy to call Python and many other languages, but I just used an example from Python here. So this is my terminal here. I started up Julia. I installed pycall using the package manager. I used pycall to import something from scipy, and then I call this function scipy.signal.gaussian. And you can see it's all really easy. Parallelism is built into the language. So I have an example here where I create an array of 100 random numbers. I map sign onto the array, which means I take the sign of every element in the array. And then if I just throw a p map in front of there, that'll use however many cores you've told Julia to use. And this is actually a terrible example because the communication overhead is dominating here, so the p map is probably slower. But the point is that it's not so hard to do. There's a profiler built in, so I profiled something here, and you can see that basically these numbers over here are roughly proportional to how much time was spent on each line. Unicode support is built in, so you can see I named this function alpha, and that can be really convenient. There's a lot of Julia code written with Unicode characters as variable names. And then a lot of it's written in Julia. Since Julia is fast, you can write actual Julia routines in Julia. So something like 70% of the actual code is in Julia, which is how I ended up here, because I fiddled around with Julia and I figured out how to do whatever projects I wanted to do. And then I found some bugs, and it turned out I could figure out how to fix them because I'd learned enough Julia to do that.
And you posted something on the message board, which is how I Googled you.
You found me. And I posted something on the message board. And I tried to use a pseudonym, but apparently I failed at that front. So yeah, so this is a bigger plus than it, to me anyway, than it seemed like it would be. So I wrote here, your types are equal to built-in types, but what I really want to talk about is that Julia is explicitly not designed to be object-oriented in the way you're used to from Python. You can basically replicate anything you can do with object-oriented in the sense that you can think of, well, let me get this. So there's something called multiple dispatch in Julia. So my example here is I'm going to create a type called myType. It has a variable inside of it called A, and then I want to overload whatever function is necessary to make it print nicely in the REPL when I do it. And the way you do that in Julia, the way you might do that in Python would be to, like, I don't know, you look up the function, it's myType.prettyPrinting or something like that. Probably has some underscores in it. But in Julia, you would overload the function show. It doesn't really get owned by myType. I just specify that when the second argument is of type myType, this is the method you should use. And so I overload this function for myType with, it prints out something, and then I do this and it prints it out. So this is sort of the way that they organize functions. Rather than having the functions associated with an object, you just say, well, if this argument is that type, do this method, and if this other argument is that type, do this method. So here's another example. I have a function f of x and y, which just subtracts them. This works for any combination of types of the two arguments, as long as subtract works for those two arguments. But I can specify that if the second argument is an integer, then you should add those two numbers. And you see I do that here, and I get different answers. So this leads to writing code that looks very different. It leads to sort of having a whole bunch of methods that have the exact same name. If you look at show, it probably has 100 different methods defined for different types. And then it's really easy to call C. You don't have to write any glue code. You just give it the name of the function you want in the library, and it works. And then, this is a little bit out of order, but just-in-time compiling sort of goes with the multiple dispatch. When I call f of x and y, I need the compiler to know what types are being used so it can generate efficient code. So what it does is it asks, have you ever called this function before with this exact combination of types? If you have, I'll use that version. Otherwise, I'm going to compile a new version just for the specific types that you're using right now. So whenever you call a function, it always compiles the most specific version of that function it can. Okay, so I'm going to give you an example of how you might try to think about speeding up some Python code and what it might look like in Julia. And so this is motivated from the pulses I showed you earlier on. We often like to generate statistics so that we can throw out bad-looking pulses. So we might take the average of this first part and look for the maximum and minimum values, and then do that for the part after the rise also. And so I'm just doing a really simple function here where I'm taking the mean, the maximum, and the minimum of this array of, I think it's 10 million numbers. And I'm doing the exact same thing in Julia over here, and I get these times. I get 54 milliseconds. So if I write code that looks the same as NumPy in writing vectorized code, it's probably going to perform about the same as NumPy. You're not just going to get a speed up because Julia is fast. But if I look at what's happening here, I'm basically calling three functions that basically just loop over the array once and either do some math or just some if statements. So I could just loop over the array once and do all that stuff at the same time, and I should be able to speed up a little bit. So I can do that in Python here. I write a loop, and I can do that in Julia over here. I just write it. It's not very hard, and I time them. In Python, things get pretty unhappy pretty quickly. But in Julia, I get a small performance boost. So basically what I want to show here is that if you want to write faster code and take advantage of Julia, you're going to not be able to vectorize stuff if that's what you're used to. You're going to have to probably write loops that look like this. And you're not really going to get anything for free. You're going to have to think. And it might actually be a little bit trickier than thinking about it in C, since you have the ability to write generic code. You also then have the burden of writing generic code. So hopefully at this point you think maybe there's something cool about Julia. So let me tell you some things that might keep you from jumping on it right away. How about that? First of all, it's pretty new language. They just released version 0.3. I looked it up. I'm pretty sure I'm right on this. Version 0.1 was released in February 2013. So not a whole lot of development time has occurred. Almost guaranteed to run into some breaking changes. If you use enough of the Julia standard library, something will break in the next few years. The package ecosystem is not really at the level of R or Python. For example, if you want to interpolate, like say you want to use scipy.interpolate, there, as of a few weeks ago, was one method for doing that that wasn't particularly fast. As of about a week ago, now they've wrapped the same thing that scipy wrapped, and so you can do that, but it's almost guaranteed that API is going to change as it gets merged into, so there's really just one API. IDE support is in the early stages. And then this is a partial list of features that are planned for version 0.4, which a pessimist might read as a list of important features that are currently missing. One is a debugger. Another is array views. So what I mean by that is if you write this statement A equals some slice of B, B already exists as memory in your RAM somewhere. In NumPy, if you do this, A will just look at the same part of memory as B, and it'll maybe have some offsets so that it doesn't look at the wrong parts. If you do this in Julia right now, it'll just copy all the elements that it wants, which is a lot slower. And so this will be a really big upgrade. Static compilation is on the table. What that means is that basically when you import packages, when you type using whatever, it's going to be kind of slow right now. It might take a few seconds because it's basically compiling the packages every time from scratch rather than compiling them once, saving it to disk, and just using that. And then strings. The whole string API is being rewritten. Currently there's like ASCII strings and UTF-16 strings. I think they said they're going to get rid of ASCII strings. Everything's going to be UTF-16 string. And I think they're going to change parts of the API. But one end result of that is that they should be a lot faster. Currently they're not really competitive with Python on string operations. Here's another big catch. So I have two examples of basically the same code we were looking at before. There is a difference between them. I'll give you guys a few seconds to see if you can spot it. I'm going to move on and tell you what the effect of the difference is. It's that it massively slows down the Julia code. I don't know if you've seen it yet, so I'm going to point to it, which is this variable s. On the left, I made sure to instantiate s with the same element type as the input array r. That's what the L-type function does. On the right, I instantiated it with 0, which is an integer. And then I passed in a floating point array. So then I add a floating point to that integer. And if you add a floating point in integer in Julia, you get a floating point number. And so the type of s changed, which meant that the compiler could not just assign a fixed type to s, and it has to handle a bunch of other cases, and it slows down quite a bit. And I can tell you that that is fairly frustrating when you're not used to writing code like this. So if you would like to learn some more about Julia or play around with it, I would recommend Googling for Julia and Getting Started, and you will find this page here, which is the Getting Started page. It has a bunch of useful information. One of my favorite things is the link way down at the bottom. It's called, I think, Learn Julia in 10 Minutes. It's basically just a list of example code with some comments on how to do a bunch of common things. I would encourage that if you're going to work on it, work with it a bit, you should read a large fraction of the manual eventually, because they really explain the ideas behind their APIs, and I definitely had some wrong assumptions going into it that led to some frustration. So I guess what I'd say is if you're using a new part of Julia, don't just look at the standard library set of functions. Read the manual that describes like what their design idea was. I would also encourage you to Google this phrase here, which I put on here just to get this site and this site. The Julia language site on the bottom is the one where you would download Julia and find those benchmarks I showed you and read a longer list of features than the one I showed you, but mostly download Julia. And then the one on the top is where you would post your question if you had a problem. And I can tell you, I don't know how the Spark community is, but I know the phrase RTFM is sort of the hallmark of the open source community in some sense. I've never seen that phrase on Google groups, on the Julia users group, and I have posted some pretty dumb questions there and gotten very polite responses from basically the core developers of Julia. And I'm sure as the community grows, they won't have time to respond to everybody's dumb questions, and somebody else will respond politely, but the community is very helpful. And since one of the main selling features of Julia is its speed, I would like to share this piece of advice I have learned about optimizing your code. And then I'm going to move on to a quick demo of another feature of Julia, and then we can have questions. So I have to move real quick. So this is called iJulia Notebook. It's, I don't know if you've used Mathematica or IPython Notebook, but the idea is to be able to mix your sort of programming, exploratory stuff, and the results, and structured text all in one document. And so it lives in a web page. Well, there's a Julia server running on that computer, and then this application talks to it. They've used the development of the IPython notebook, which was written in a very general way, so it could use different backends. So basically, the front end is IPython notebook with a reskin, and then they've gotten some pretty cool results. And one of the neat things about Julia is that they're able to learn from, all the other scientific computing projects that are out there, and that they're starting from scratch, so they can sort of incorporate all the cool things that everybody in Python and R have done, or a large subset of them, we'll say. So what's happening is I have some code here, and I hit Shift-Enter, and then it evaluates the code, and it puts the response right below it. And then I already have all the text that I typed and stuff. So that's just whatever, some expression that gives some number as an example. But this is a cooler example. This is a plot. I'm using, this is matplotlib, a Python package, but being called through Julia. It's called pyplot in Julia. And then the plot just shows up in line here. And I guess the resolution is a little bit different, so things are very zoomed in. But you can see the plot just shows up in line rather than its own window. And this is because the plot object that is returned has defined the write_mime function. And so it's not very hard to get this kind of behavior. And so I have an example here where I'm going to create an HTML type, and then I'm going to overload the write_mime function so that it knows how to display when it has sort of a rich display environment available to it. And then I'm going to instantiate an HTML object, and you can see it automatically parses the HTML and displays it in a nice way. So this is very easy to implement, and it's been done very easy or early on in Julia's development. So they're hoping that a large fraction of their package developers will support this kind of display in IPython Notebook. And then another thing I wanted to share with you is, at least for me coming from Python, I was used to, you look up whatever function you're going to use, you get whatever it returns, and then I have this object. I don't know a whole lot about it. I know it was returned from the function I thought I wanted to use. So I type the name of the object, and I type period, and I type tab, and it brings me up a list of functions that I might use. And that's one of the ways I can start to learn about what I might be able to do. Since Julia is explicitly not organized that way, instead you have these functions methods with, which will tell you what you can do with a type, and then methods, which will tell you all of the different methods of a function. In this case, the function name / is division. And one of the cool things is it gives you links to the actual, I'm not on the internet. Okay, fine, that didn't work. It gives you links to the actual code on GitHub, the actual Julia source code. So that's all I wanted to say. So if you have any questions, now would be a good time. Yeah.
Who's the organization behind Julia?
So it's run as a project on GitHub. The core developers, as far as I can tell, consist mostly of people at MIT. There's a Professor Edelman, and I think a couple of his graduate students. And then there seem to be another couple of heavy users / developers scattered throughout the world. Like there's a guy at Facebook and a university in Texas, and I guess there's a guy in somewhere in Southeast Asia who does a lot of stuff. But I think the real core and the team that started it is at MIT.
Yeah, so they're not necessarily from MIT, but they're so three people are supported to work on it full time through grant money, and I think now that it's doing well, that they'll be able to continue doing that.
Okay.
But there are, there are at least 20 people with more than 100 commits to the core language. So it's, it happens to seems like it's people who, they want to write a really specific package, you know, for image processing, and then they get sucked into contributing to the language.
So, thanks.
So you started to make a statement about how the language was not originally designed not to be object-oriented, and then you went into the discussion about the multiple dispatch.
Yes.
Could you expand on the decision not to make it object-oriented a little bit more? Or?
So I'm speaking a little bit outside of my expertise here, but my impression is that there is a substantial subset of the sort of software design community who believes that object-oriented programming is not really a great way to organize your code. And that the way Julia is doing it, which is, I think I'm forgetting the word here, but basically the way Julia is doing it is sort of will lead to better code design. And then the other statement I would make is that multiple dispatch is, in some sense, an extension of object-oriented programming. You can think of object-oriented programming as dispatch on the first argument. So I have functions that have the same name, but they belong to a type, and I usually pass that as self, and so that's dispatch on the first argument. Multiple dispatch is an extension in the sense that it's dispatch on all the arguments.
I think that is one of the anti-pattern that he can include on his book.
Yes.
How is variable memory handled? Is it going out to the operating system malloc each time you allocate a variable and free when the variable is released, or is there some type of heap cache mechanism?
So I think this will answer the question. It currently has a stop the world garbage collector. And I know that there is a lot of discussion about at least adding different options for the garbage collection, but I don't know if that answered your question or not.
Yes, it looks like on the exit, on the free portion, they store them up and process them in the garbage bin.
Yeah.
On the allocation of the variables memory, is it going out to heap?
Don't know the answer to that. Sorry. Yes.
Can you call functions in Julia from Python?
Yes, although I haven't tried it. I have read about people doing it. So I don't know what it looks like, but I assume it's not particularly hard. There's definitely been a lot of work to be able to call Julia from many different languages. Let's go here.
I saw the results for Go was just about as fast as Julia. Have you compared Go with Julia?
I have not compared Go with Julia. They had it obviously in the benchmarks. My impression is that Go is relatively typed, and so in that sense you'd expect it to be pretty fast. But I haven't really done anything with it myself.
Have you worked with the macros or the heap functions? Oh my gosh.
I have played around with them a little bit. So for everybody else's knowledge, he's asking about macros, which is what they would call a metaprogramming capability, or writing code with code. And so macros are basically like functions, except for when you pass something to them, they don't get the result of the statement you put next to them. So let me just give you an example here. Oh, yeah, okay, there we go. So it doesn't get the result of the statement. It doesn't evaluate log of 4 and then pass that to the macro. It parses the code that I typed in there, log 4, and it passes an expression object to the macro. And that way you can do things like show right here that I had typed log of 4, and then tell me the answer, which is something that is not super straightforward to do in Python, at least my understanding. And I have not played around with it enough to find a lot of applications in my own work, but there are a large number of macros in Julia that are super useful. And I have seen many examples of people using this sort of capability to enable speed boosts that are much faster than the way you would do something in C, not necessarily because Julia is faster, but because it was easier to write code that wrote really efficient code in Julia than it was to write the really efficient code in C, if that makes sense. Yes.
So other than the scientific organizations, like what are the other industries who is going to be the early adapters of Julia?
Let's see. I have not seen a ton of action on the message board that would give me a good answer for that. I will tell you that they are very committed to MIT licensing most of their code, which is a very open license. It's not viral like GPL. And they often ask package writers to MIT license their code, and that's explicitly because they would like people to be able to do whatever they want with it. And I think they view that as an industry-friendly move. And I will say that I know that there are at least a few people at, like this developer John Miles White, I believe, is at Facebook. So he's interested in, you know, big data type things, but I haven't seen a lot of stuff that would tell me which people are adopting it. I've seen more, there are a lot of, I think the early adopters that I've seen are or at least they're talking about the early adoption, are more academic types.
What sense I got was that operations research, like linear programming, is one place where it's being considered more seriously in production. And I think part of that has to do with the fact that they're able to, you know, their DSL uses macro. The fact that it uses macros, they're able to rewrite it more quickly to get to the sparse matrices that they have to solve than even the other commercial options. So that's, you know, an area where it seems like there's a lot of traction in commercial application.
Thank you. Thanks. I think, is that it?
Thank you, Galen.
Thanks.
And thank you all for coming. We'll see you next month up in Boulder at Atlas. Drive safe.